We have seen several ways how to control the cell cycle in this picture. It doesn't mean that all of them are required at every single level of cell cycle. A combination of few of them are required at each point. So when you start to read articles, you're going to see that a combination of few of them is required for some certain level of them. So when you're at the G1 phase, uh, well, if a cell is going to wait, if a cell is going to, let's say, not go into the proliferation, it can wait here. G1 phase is the phase for that. Okay. It can go to the S phase and continue cell cycle, or maybe it can go to G0 and wait there for some time, or it can go into the terminal differentiation, like in the case of a neuron, for example, which it will never go back to the cell cycle. Or if you talk about the liver cells, they will spend most of their time here waiting, only and only when there is a liver damage that they're going to go back here. So you can induce the proliferation here in these cells, in some cells, but when they are terminal differentiated, no, you cannot induce them anymore. Okay, how do they happen? How do they make sure that this is not going to happen here? So, for example, you can get rid of the cyclins by proteolysis. If there is any cyclin CDK complex left, you can block them by P27. And there are some other CDK inhibitors. By the way, these are CDK inhibitors. So that way you make sure that it's not going to be active anymore. What pushes here this point G1 to S is an external signal usually that we call mitogen. Okay? Of course, the internal conditions must also be okay, but being a healthy large cell is not enough for division. It should be also signaled from outside via a mitogen and should be taken by the cell surface receptors. And then the S phase starts. Okay, when the S phase starts, we know that the S phase is the synthesis phase. And in the synthesis phase, it is not only synthesizing protein, because protein synthesis is done all the times. What is really synthesized here is the DNA. And DNA synthesis is done in a highly controllable way, because the moment that S phase starts is the moment that DNA replication starts. So this is a chromosome, and these are the origin of replications. We know that in a chromosome, it cannot start from here or here randomly. It should start some very well-defined regions called origin of replication. And for a piece of DNA, if you're going to call it of chromosome, it should have an origin of replication. If there is a piece of DNA, but there is no origin of replication, it's just a DNA fragment. So not every DNA fragment can be called a chromosome. And we are going to see vectors in detail. We already have seen some vectors. Without the origin of replication, a vector is not functional at all. These origin of replications, they are the regions that the DNA replication will start, and they don't always start at the same times. Maybe some of them are going to be induced earlier, some of them are going to be induced later, but S phase will not finish before all of them are replicated. Okay, origin of replications, they don't stay unmarked. They should carry this mark on themselves. So even if there is no DNA replication, even if there is no idea of DNA replication, the origin of replication is anyway marked with a protein complex that is called ORC, origin recognition complex. So this is the natural way, this is the default way. Even if it's in G2, even if it is in G0, this is how it waits. But this way, with the origin plus ORC, this is not active yet. To activate it, first you need something that is called CDC6. So CDC6 is produced in the cell cycle in the early G1, and it is going to bind to this ORC complex. And later, the DNA helicase will bind here. So if you have DNA double helix, what you should do is first you have to melt it. Without melting the DNA double helix, without opening it, DNA replication will not start. So, and we know that this melting is done by DNA helicase. So joining of DNA helicase is very critical. It doesn't join onto the ORC complex. It joins just next to the ORC complex. It also removes the CDC6. And next, the firing is triggered by the SCDK. The SCDK because it's also a kinase itself, it phosphorylates the ORC and it phosphorylates the helicase, so it starts to work, plus DNA pole joins. So this is the moment that the S phase starts, okay? Because literally now it pulls the trigger and the DNA polymerases start to work in both directions. Okay. By the way, the SCDK not only starts the DNA synthesis, but it also phosphorylates the CDC2. Because when SCDK phosphorylates the CDC6, it actually degrades the CDC6. It makes sure that CDC6 is going to be degraded. It's not going to be used again, because if it is used again, if in case there is another activity here, before the S phase finishes, another S phase will start. So the DNA replication will look like this. First, it is the G1 phase, and then there is the S phase. DNA replication is going on. And in case there is a loss of control, in case there is something going strange here, it will start another round of replication here in the origin of replication. So two replications happening at the same time. This is going to create a faulty chromosome. This is going to be a chromosome damage. And it's dangerous, it should be prevented. This is why CDC6, which is inducing the ORC complex and helicase, should be degraded. No more CDC6. So this SCDK not only starts this round of cell replication, but also prevents another round of cell replication. Okay. By the way, in some cancer cells, this really happens. A cell cycle, well, before one cell cycle finishes, another cell cycle happens in the same time. Another replication happens at the same time. So they have very strange chromosome numbers. This is normal. This is why we don't trust the cancer cells much, at least not all of them. Okay, this is how the S phase is controlled through the origin of replications. And in the G2 phase, it is right before the M phase, so it waits, it checks if everything is okay. Before the mitosis, it checks if DNA is replicated. And here, it is kept inactive by V1. Here, the passage from G2 to M phase, the signal is given by the CDC25. Okay? And when there is a DNA damage, the CDC25 is inhibited itself. Okay. So this is how the DNA damage is controlled at every single level. Now, when we come to M phase, we know it is fast and we know it is very sharp. One thing I want to talk about its being sharp, we have seen the graph. The graph is never this way. The graph is always very sharp. The decision is taken extremely fast. This is the activity of MCDK. It's because there are several mechanisms acting on the cyclin CDK complex. It's also because once the cyclin CDK complex is active, it is going to activate itself. So we know that the CDC25 activates the cyclin CDK complex, and in return, the cyclin CDK complex will activate more CDC25. This is a positive feedback loop. This is why, even if there is one single active cyclin CDK, it is going to amplify its number rapidly, and it's going to increase the number very fast. And we know that V1 is suppressing the cyclin CDK activity. Once it is activated, it will also go and block the activity of V1. This is why once the signal is given, it is given really sharp and it activates everything abruptly. So from this one single cyclin CDK, you're going to create a lot of cyclin CDK activity, and they will start mitosis all at once. So yeah, let's continue it later.